This video is about momentum and actually the conservation of linear momentum. And momentum is defined here as the product of mass and velocity. So if an object is moving, we say it has momentum. The more mass of the object and the more velocity, the more speed of the object, um, the more momentum it has. And of course, the units of mass are kilograms, velocity is in meters per second. And so kilograms times meters per second, the units for momentum are kgm over s. And I'll just note here that we do want velocity, not speed. And so direction matters with momentum. Momentum is also a vector, and so we give direction when we write the momentum of some object. Now, that's a simple calculation. Um, and what we really want to talk about is the conservation of linear momentum, which states that if there are no net external force, I'm sorry, if there is no net external force acting on a system, then the total momentum of that system is conserved. And so typically we'll see two objects that collide, and we'll look at the momentum. Let's just take a look down here at this example here. So on the left side, we have two objects that are about to collide. This 3 kilogram object's moving to the right at 8 meters per second, and the 5 kilogram object is moving to the left at 2 meters per second. Now we can calculate the momentum of these. That's just mass times velocity, mass times velocity. But what we're saying here is that when these two objects collide, as as long as there are no net, as long as there is no net external force acting on this system of objects, then the total momentum will stay conserved. It'll stay the same. Um, Not for each object, but for the total of the system. So after they collide, the 5 kilogram object is now moving to the right, 4 meters per second. And we want to know what is the velocity of the 3 kilogram ball. And so I have the equation over here, which I'm going to cut and paste over here. So let's look at it this way. So the mass of object one, I'll just call this one object one. This is 3. The velocity is 8. This is the 5 kilogram object. The velocity is -2 because it's moving to the left, equals 3. And we don't know the final velocity. And here we have 5 with +4. And so let's take a look at the notation here. I typically write the left object as mass 1 and this one as mass 2, which they're the same masses here. This is just after the collision. Okay, this is read as the velocity of the first object, initial, and this is the initial velocity of the second object. Okay, two masses. This is the final velocity of the first object and the final velocity of the second object. So 3 times 8, that's 24. 5 times -2 is -10. 3v1f, and this is 20. So this is 14. It's -6. And so this is -2. But we should write this as 2 meters per second to the left. That is the velocity, the final velocity of the first object. So it would be moving this way, 2 meters per second. And so again, this is the conservation of linear momentum. The total momentum of the system before the collision is equal to the total momentum after the collision. In other words, the momentum is conserved. So there are two types of collisions. There are elastic collisions, which means that the kinetic energy is also conserved before and after the collision. But typically, many of them will be inelastic, where kinetic energy is not conserved; it's lost in the collision. And there's a special type called perfectly inelastic collisions, which we also name as hit and stick collisions. They hit and stick together. So there's some examples on the homework, but we kind of start the equation the same way. But if they hit and stick together, you can just combine the two masses together with one final speed. And sometimes they're actually stuck together in the beginning and then they kind of separate. So you can also kind of have this equation in reverse, something like m1 plus m2 v initial equals m1 v1 final plus m2 v2 final. Could have something like that as well. Okay, so for example, one, let's determine is this elastic or inelastic? And so that means if we were to get the kinetic energy of object one and the kinetic energy of object two and add those up, that would be the initial kinetic energy. And if we got the kinetic energy of these two objects and add them together, that would be the final. And so let's see, 3, 8, 5, and 2. Trying to remember these. This is 3, 8 squared over 2, 5, 2 squared over 2. Remember that kinetic energy or energy is scalar, and so we don't really need the negative 2. We just need the speed. So this is 8 times 8 is 64 over 2 is 32 times 3, 96. That's 10. So this is 106 joules. And let's get the kinetic energy final. So 3254. 3 with 2 with 4. So looks like 6. Um, looks like 8 times 5 is 40. I'm just laughing because my wife held in a sneeze right now. She's walking by. Okay. So even if I made a mistake somewhere here, I'm pretty sure that the kinetic energies were not equal. Um, yeah, so it started off with more kinetic energy. It ended with less kinetic energy. So some kinetic energy was lost. Regardless, because they are not equal, because kinetic energy was not conserved, we call this an inelastic collision. And I think that's it.